There, it's working.
Are we back? I can never tell. I can't tell from my end. Isn't there like a red light or something?
Yeah, it's
good
going.
Okay. I don't want to lose this later on. So we're going to start. I'm going to review the Calc 1 stuff. I'm going to review how you did everything in Calc 1 because we need to take that and build it up to get to here. I'm not going to start with the assumption that everybody remembers the details, and it's actually the details that are the important part. So in Calc 1, okay, what we did was we said let's consider y equals f of x, and we'll do the simplest version. We say, quote unquote, area under the curve. The term area under the curve literally means curve to axis. We could also be bound by two curves. We know that. I could have two curves intersecting and I have to find the points of intersection. Great. But let's start with this simple one here. This is not a geometric shape. Okay? So what I have to do here is figure out something else. So the first thing we decide to do is partition this randomly. And what I mean by random, I want to make rectangles of random widths. Okay. So I've just created a series of partitions. Okay, and the term partition we use in mathematics all the time, but a lot of times people don't know exactly what it means. I'm going to use this building as a perfect example. Okay, I come from a family of contractors. It sounds kind of funny when I tell people that. I have brothers, father, uncles, cousins. They're all contractors. I'm the only one who decided to go to college. You know, I didn't want to get my hands dirty. But I've come from a family of contractors, so I know a little bit more than the average person about construction, and they actually asked my opinion a lot on this building. You see, that back wall, that's an important wall. It's called a load-bearing wall. This wall here is not. That wall here, we knock those walls down, nothing happens. They are partitions. It would be as if we had one gigantic room and we just randomly put a partition here. A partition literally is, think of it as a divider. Okay? It's just a divider, it doesn't do anything else. So I'm going to randomly put dividers in here. That's what that means to be a partition. And I'm going to make them into rectangles by choosing random places in the height. So maybe this one I'm going to go about there, and this one maybe from the left, and this one maybe, all right, you say right, left, and kind of here, and maybe here. Okay. The crazy part is if I randomly partition the widths and then randomly select a place on top, it's actually mathematically possible that the area under the rectangles could equal the area under the curve. It's actually possible. Now, it's not very likely because it was completely random. But if I said add up all of the areas of the rectangles, would that be a reasonable estimation of the area under the curve? Yes. That would be a reasonable estimation. So the question is, how do I do that? Well, first thing we did was we said, if this is x0 and that's x1 and that's x2, eventually that's xn because I have exactly n partitions. So let's call this one here. Let's say that goes from xi minus 1 to xi. It's the ith rectangle. And that's the one I want to concentrate on. If I can figure out the information about that, it's easy to extend. If you remember when you were finding areas or finding volumes by rotation and things in Calc 1, you always took the arbitrary slice. We always called it the ith slice. If I could describe it, then the rest was really easy to do. Okay? So delta xi is xi minus xi minus 1. This is delta x1. It's x1 minus x0. Delta x2, x2 minus x1, and so on. So what is the area of this rectangle? Well, usually what we do is we pick a random place within the rectangle to find the height, which I did. I did not choose an endpoint. I picked a random place. And that place here we usually call wi. The place in this one I'm going to call w1. It's the first rectangle. That I'm going to call w2, w3, and so on, where wi must be between xi minus 1 and xi. It could be either endpoint, it could be in the middle, it could be anywhere in there. But that's where I measured the height. Therefore, I can now say the area of the ith rectangle is equal to f of wi times delta xi. Okay? Everybody cool with that? Then I can say the overall area can be estimated, and this is definitely an estimation, this is not an equals. I mean, Could it be? Yeah, but it'd be like a 1 out of infinity probability. From I equal 1 to n of the AIs, which is the same as saying from I equal 1 to n of f of wi delta xi. And overall, we'd say x is ranging from a to b. Great. That's an estimation. I want an equals. So this is what I talked about before. I need delta x to approach 0, but since all of the delta x's are completely random, I need the largest delta x. When we talked about this, my shrink ray, I need the largest delta x to approach 0. So if the largest delta x is approaching 0, then there's a new largest, and it's approaching 0, and so on, and so on, and so on. The easiest way to state that, what's happening, is we say, let's take the limit as the norm of the partition. The norm of the partition, okay? That's the largest width approaches 0. That's kind of like saying simultaneously all the delta x's are approaching 0. No, I can only do one at a time. But if I said the biggest one's always approaching 0, then eventually they're all approaching 0. Of this, and this is called, you guys remember? This is called the Riemann Sum. You never calculated this. Oh my God, that'd be a nightmare to calculate. No, we said we're going to define this to be this thing called a definite integral. Now, that didn't tell me how to calculate this. We defined the definite integral to be this limit. The fundamental theorem of calculus was where we learned that this was the antiderivative evaluated at the endpoints. That's fundamental theorem. But I had to do this first, okay? So we understood the geometry that was going on here is really not that complicated. Do you all agree? It's just not that bad. Okay, great. So now I want to go back to that picture and I want to change something now. Everything I said is still true, everything I said is still correct, but what I want to do is within each rectangle, I want to subdivide within the rectangle itself. So I like to go now, these guys and these guys don't have to be the same, but I want to make the same number of them. I made n partitions horizontally. I want m, different number, m partitions vertically. And again, completely random. So let's go back to our ith rectangle. And I want to concentrate on that one right there. Okay? xi, those would involve y's, wouldn't they? So what is that guy? Erase this for a moment. I'll just sort of say it loosely. This was delta x1, this was delta x2, this was delta x3, and so on. But that's not delta x. It's smaller. We're going to call that delta a ij. In other words, it came from the ith rectangle this way, and then the jth one going up. Where the I and the j are completely unrelated. One was horizontal movement, one was vertical movement. Okay? Would it be reasonable for me to say that I could estimate my area by adding up all of these guys now? So down here, this is capital A11, and then this would be A12, A13, A14, blah, blah, blah. This would be A21, A22, A22. This would be A31. If I add up all the little rectangles, would I again get a reasonable estimation? Yeah, because if I add up all these rectangles, I get delta x1. Oh, okay, so it is correct to say that delta xi would be the sum from j equal 1 to m of what? Of delta aij. I know this is a bit confusing, but let's kind of keep track. What did I just do here? I just said, okay, that's delta ai1 plus delta ai2 all the way to delta aim. That's ai1, ai2, ai3, ai4, all the way up to aim. Does that make sense now? Oh, if I add up all of these guys, you notice I didn't change the I. Then I just came up with the ith, rectangle horizontally. Cool. But I can now do this as a double sum. Yes, Sam?
Wouldn't the left side need to be multiplied by f of w sub I, so it's the area as well of the ith rectangle?
Well, but we haven't calculated, I just want to, did I lose
Because
something?
the left side should be area if the right side's also area.
Oh, no, right, but what we're doing is, what is this height? This height is the f of xi, right?
Yeah, f of w sub I.
But all I wanted to do was just reproduce, did I just, hold on a second, I think Sam said, hold on, delta xi. Oh, yeah, I see. Sam, this should also be the, yes.
Okay.
Yeah, thank you. The whole area was equal to that, sorry. Yes, he's absolutely correct. And when I added all these guys up, what did it do? It just gave me back that that ith rectangle. Now, we're gonna do this as a double sum because I have to add it horizontally and I have to add it vertically. Again, I want to add all of these guys up, finish that sum, and then move on to the next one. Add all of them up, finish that sum, and move on to the next one. You with me? It sounds a little tedious, but it's going to create notation that's going to make things much, much simpler to understand in the long run. So I need to take the sum from j equal 1 to m, okay? Of these guys here, and then take the sum from I equal 1 to n of all of this here. Well, technically, delta, now if you look at it, what is delta aij? Well, that's delta xi multiplied by delta yj. I'm actually taking the little individual pieces. So I have the sum of a sum. Okay, I have the sum of a sum. Remember, if I add up all the delta y's, then I get, if I add up all the delta y's, then I get the height. So this is kind of weird. Can I say then the overall area, can I still limit as norm of the partition approach to 0 of the sum from I equal 1 to n of the sum of j equal 1 to m of delta, I'm going to write it in this order, delta yj, delta xi, because technically you're doing that, and when I add up all those, that gives me my f of x. So I'm starting at I equal 1. I'm on the first rectangle. When I add up all these guys, that will give me f of w1 times delta xi. Now I'm going to go to I equal 2. And I'm going to start over, add up all of these guys again. Is that overkill? Yes, absolutely it's overkill. We already know an easier way. Here's the point. What is the norm of my partition now? It's not the widest width. It's the largest area. Okay, because now I'm partitioning it into little rectangles, aren't I? Before, I partitioned this one only. But now I'm doing like a grid. This is looking more like a checkerboard now, isn't it? So now the norm of the partition becomes the rectangle. Later on, we're going to do this in 3D, and the norm of your partition is going to be little prisms. But everything else stays the same. This is equal to the double integral, I'll just say 1 dy dx. Because I don't have anything here, so I'll just call it a 1 for now. Now, what are my limits of integration? Well, the inner one is all y, so y in my picture is going from basically 0 to f of x, isn't it? And x was going from a to b. Now this, again, this is going to look a little bit weird at first, but when I look at this problem, when I'm looking at this problem, this is inside the problem. So I'm actually going to work inside out. Think of it like parentheses. Well, can you all integrate 1 dy easily enough? What's the integral of 1 dy? that just be y evaluated from 0 to f of x? But this still lives inside this. It helps do that. Now, when I evaluate y from 0 to f of x, what do I get? I get f of x minus 0. Huh. Look familiar? Isn't that what we said this is? Isn't that the integral? Wow, that sure took me a long time to get what I already knew from Calc 1. You're right. You would never do a Calc 1 integration as a double integral. You would never do that. But I can, and it will always produce the same answer. So why would I ever do a double integral? Because your integrand is never going to be 1. It's going to be a function. Ah, so I'm going to change everything you just ever did in Calc 1. Okay? When I used to teach remedial algebra, and I would try to, particularly do the geometry part, and I try to teach them about shapes. You remember doing things with, surface area. Surface area confuses people, because if I said, what's the area of the board? It's a rectangle, base times height, piece of cake. But now I say the surface area of the room. Why does that cause confusion? Because I'm in 3D, I got to add up a bunch of things. It's not the same calculation, is it? I'm doing a bunch of areas. And then when we say volume, well, I'm still using the base times height, but now there's a third dimension. There's confusion when you're in lower level algebra class going from 2-dimensional stuff to 3-dimensional, because you're also still doing areas and stuff. Yikes. So I want to find the area of this floor. You multiply the dimensions. Let's pretend that corner is not cut out. When I would teach people how to do volumes in general, I'd say, think of it this way. Let's pretend, because back in the old H building, I didn't have to, we actually had 1-by-1 tiles. It was the easiest because I would use these as analogies all the time. It literally looked like a graph paper. Imagine this floor, we're going to cover the floor with tiles, and they're all 1-by-1, 1 foot by 1 foot tile. So if I asked you what is the area of the floor, would that be equivalent to how many tiles did I just use? Do you all agree with that? Yeah, piece of cake. So now, what if I said, oh, these are not 1-by-1 tiles. You're standing looking at the tile, but then I pick it up and it's actually, you're standing on top of a 1-by-1-by-1 cube. You didn't know you were. You were standing on top of it. But we have a 1-by-1-by-1 cube. So instead of asking you what's the area of the floor, I could ask you what is the volume of all of these cubes. You'd say it's the area of the floor times 1. But now you made it a volume problem, didn't you? So imagine I said, go back to this picture here. You asked for area, but I don't want area. I actually have a 3-dimensional solid. It's coming out of the board, and it's exactly 1 unit thick. Does everybody see what I'm getting at? I have a 3-dimensional solid. It is 1 unit thick. What is its volume? Well, wouldn't it be the area of the thing times 1? But now it's a volume. I would need to do this as a higher integration because I'm doing something 3-dimensional. So you could now also argue this is the volume of that shape that's 1 unit thick. Okay, so now let me change it one more time. This is still the region in the xy plane, but now I have some, I don't know, fluffed bed sheet. I have a fluffed bed sheet over this shape. And I want to know what is the volume under that bed sheet. You with me so far? How do I answer that question? Well, actually, I'm going to go start from scratch. I have a volume z equals 0 is the xy plane. I call this my roof and this is my floor. This is my bed sheet I'm standing over. I have a region in the xy plane. This is my generic region in the xy plane. The universal notation we usually do is we put r with a subscript of xy. That means the region in the xy plane. Not real numbers, just the region in the xy plane. If I asked you what is the volume of this thing, you would say the volume is the double integral over the region in the xy plane of f of xy dA. What is dA? dA is dy dx, or it's dx dy, depending on what order you choose to integrate. How would I know what order to choose? If I went back to Calc 1 and I asked you what is the area of this region, now in case you forgot, think Calc 1, okay? I asked you what is the area bounded by all this stuff. Absolutely every problem that exists can be integrated with respect to x or with respect to y. Most of the time you integrated with respect to x because it was easier, because all of your boundaries were given y as a function of x. But what if all your boundaries were given x as a function of y? Well, then you're probably integrating dy, much easier. But every problem that exists can be integrated both ways. You chose whatever one was easier. And most of the time it was probably with respect to x. But it wasn't always with respect to x. But the fact is that every region that exists can be integrated both ways. One is usually more efficient than the other. So you have to decide, do I want to make this into vertical rectangles when I set it up, or do I want to make it into horizontal? That's your choice. Oh, and then that will determine, do I want to go dy dx or dx dy? The variable that comes first is the one you're integrating first. So if I do vertical rectangles, it's dy dx, because I'm integrating x last. Horizontal rectangles, it would be dx dy, because I'd be doing y last. Just like, think Calc 1 for a moment. So a double integral is primarily used for volume. What was a single integral primarily used for? Area. Could I do other things? Of course. But that was the first application you learned. The first application of a derivative was to find the instantaneous rate of change, slope of a tangent line. But there are many other uses. The first use of the integral is area. Okay? That's the first use, but that's not the only use. But that's our first use. So now the double integral, the first use would be volume. We're going to use it for other things. We're going to use it for surface area and other things. Now, that's the application. I want to get into the how. How do you actually evaluate a double integral? Because this is what we're going to do. Once you can do a double integral, then you can do higher integrals too. It's not really a big deal. So if I ask you to do a Calc 1 integration, does that have to actually represent something? Just hypothetically, if I said, all right, I'd like you to go from -2 to 5 of sine x plus e to the x minus 3x squared. Okay, I want you to do this integration. Does there have to be an application? Does it have to actually go with some other question, or is it just an exercise? Yeah. Almost 100% of the time you integrated, you just were integrating something with there was no plan, it wasn't going anywhere. You were just practicing integrations. Then you were told, okay, find the area or find the volume by rotation. You were asked to do an application. Then you set up the integral and you evaluate it. But if somebody asks you to evaluate an integral, they're just saying, do this. If I put limits of integration, does it matter whether it's positive or negative at this point? If I just said integrate that, do you care if it's positive or negative or even zero? No. If I said find the volume bounded or find the surface area or find the area bounded, now, okay, I probably should get a positive number because I'm setting up the problem to calculate an area. See, that's when it has to be something because you're setting it up. But if I just said evaluate this, everything's fair game. So that we often make the mistake of saying, oh, no, I got a negative answer, I can't get that. Why? You're just evaluating an integral. Positive or negative doesn't really matter. So we all know how to evaluate a single integral. What I want to do right now is evaluate a double integral. So let's consider something. Let's say I've got x squared, let's say 4x squared y minus, I want to keep this simple, minus 2x dy dx. Y is going to range from 1 to x, and x is going to range from, let's say, 2 to 3. Okay. This doesn't have to represent anything. I could work backwards and say it represents a volume, and there would be nothing wrong with that. Okay? But I just want to evaluate this. So it's the how. So when I'm looking at this, my eyes focus on this first. When I asked you to do a second order partial, you picked one to do first. And we saw with partials it really didn't matter, but with integrals it actually does. So I've got to do the y first. Now, how do I integrate? Well, this is brand new, but it shouldn't stump us. If I have f of xy equals, I'll keep it simple, x cubed y to the fourth, and I want the partial of f with respect to x or the partial of f with respect to y, when you looked at this, you said, I'm going to think of y as constant, and I'm going to differentiate the x part. And that is a correct way of looking at it. So then you said your answer was 3x squared y to the fourth. On the second one, you said, I'm going to look at x as being constant, and I'm only going to differentiate the y. So therefore, you got 4x cubed y cubed. When I'm looking at this, I'm going to integrate with respect to y. Therefore, I'm going to treat x as constant. It's exactly the same in reverse now. Oh, okay, so let's see what we get. I'm going to integrate with respect to y. So in a sense, almost like ignore the x. So what should I get?
2x squared y squared.
Yeah, so this would be 1/2 y squared, so I'm going to get 2x squared y squared
Minus 2xy.
minus 2xy, because I'm treating the x as a constant. Oh, now how do I know if I did it right? Every time you integrate it, there is one question that a Calc 1 student should not ask. Did I integrate correctly? And my response will always be, we'll take the derivative. Right? Remember in baby algebra? Did I factor the polynomial correctly? Multiply it back out again. Isn't that the instruction you would always get? Oh, if I multiply it back out and I get the original polynomial, then I guess I must have factored it correctly. Did I integrate correctly? We'll take the derivative. Do you get back the original integrand? If you did it correctly. So how do I know if I did this correctly? Differentiate this with respect to y, because that's what you integrated with respect to. Oh, let me do the partial with respect to y. Okay, got it. Yeah.
Why do you use the ordinary differentials for like the dy dx?
Because you're only integrating one thing at a time. So yes, good. That's a good question. There's no partial derivative notation in an antiderivative, because again, you're only doing it that one variable at a time. It does seem reasonable. It certainly seems reasonable that we should be able to do the other one. But again, for antiderivatives, it's always the ordinary. By the way, that's a great question. I haven't been asked that one in a while. Now, from 1 to x, and then my dx is staying on the outside. So it's sort of the problem within the problem. Now, when I am done with this, I'm going to show you all the places where people sometimes get confused. So therefore, I want to avoid confusion. There's certain little tricks you can do. I had an orange. Ah, here it is. There's certain little tricks. You see, I now need to evaluate this at from 1 to x. But where does the 1 go? Where does the x go? Does it go into the x or to the y? That seems like a pretty important thing. Do you agree? X is on the outside. X equal 2, x equal 3. Y is on the inside. This is y equals 1 to y equal x. You never have to do that, which is why you should always do that at first until you get really comfortable and get used to it. The most common mistake people make is when they evaluate, they put it in the wrong variable. Because I have choices. It sure looks like I have choices, doesn't it? This is y equals 1 to y equals x. Therefore, I'm going to replace the y variable with these guys, not the x variable. Okay? And it's particularly confusing when those are constants. Then it really seems like it doesn't matter. It actually does matter. So this will be equal to the integral from 2 to 3 of what? Well, we start by evaluating at x. Everywhere I see a y, I'm going to replace it with an x. So that'll be, what, 2x to the 4th minus 2x squared minus, now evaluate, everywhere I see a y, I'm going to put a 1. So 2x squared minus 2x. Now, I'm going to stop right here for a moment. If I have done this correctly, I now have a single integral, which means I can only have one variable, and that variable better match my instruction. I cannot have any y's at this point. If I evaluate at the wrong place, I might still have y's, and that's kind of a clear indicator, okay? Now, can I clean this up a little bit? I have 2x to the fourth minus 2x squared minus 2x squared, so plus 2x. So if somebody walks in the room right now and they see this, are they going to be intimidated? No, that's just a simple single integral. So a double integral will at some point always produce a single integral. All right, so don't just finish it off. So 2/5 x to the 5th minus 4/3 x to the 3rd plus x squared from 2 to 3. Get out your calculators. Let's make sure we get the right answer. Now, I'm going to assume you're going to use a cheap calculator to do this. You're not going to sit there and do this pencil and paper, right? So some guys go, okay, 3 times 3 is 9, and then 3 times 9 is 27, and 3 times 27 is 81, and 3 times 81 is 243, and then 243 times 2/5 is 486 and then write that down. No, do it on a calculator. First of all, it'll be a little faster, and you probably won't make a bunch of errors. Right? So let's just do the answer here. You're done with the calculus, now just plug and chug on the calculator. Anybody got a number yet?
Have a decimal number.
Well, should be probably something with,
Yeah.
at worst, 15ths. So,
961 15ths. 961 15ths.
does anybody else get that?
Yeah.
Now, you just brought up a great point. I can use my fraction key, and that's absolutely correct. But it's probably not very fast because I have to enter so many different things. So what I would do on my calculator, I'm lazy. That's the answer I want. But on my calculator, I'm just going to enter the 3 and the 2, and I'm going to have decimals. I always remind people. Something that is there, and I show this even in pre-algebra classes. My final answer might simplify. That maybe simplifies, maybe it doesn't, but at the very worst, my final answer is going to have a denominator of 15. Do you agree? Here's what I say. This equals ID, that stands for equidecimal. And equidecimal must be something over 15. This is what I actually do. If I have calculus students who will mind-numbingly spend time trying to reduce each fraction as they go, and then figure out common denominators and do all this stuff by hand. I'm like, why are you doing that? It's forever. It takes forever. No, calculate the decimal. It's equidecimal. Equidecimal equals something over 15. So how do I find the numerator? Multiply equidecimal by 15. So this problem from beginning to end, if I'm doing it on a cheap calculator, 15 seconds, 20 max. It just can't take a minute. There's no possibility I could take a minute to do this kind of calculation and still get the right fraction. Because I'm not wasting time on the minutia. I want to get the answer. So have your equidecimal, and you already know the denominator. Now, what if it did reduce? Great, then I'll reduce it. No worries. You know, if I end up with even number over even number, I can probably cancel it too. Now, if you use your fraction key and you're comfortable and you're good with it, great. Then you'd say fraction key 2/5 times 3 to the 5th. And use fraction key throughout, and then your calculator will spit out the fraction. And I love that. That just takes a little longer. And what is the other potential issue if you're using a fraction key? Does anybody know? There is one. What if? That's supposed to represent big. If you have really large numerator and denominator, your calculator is going to convert it to a decimal anyway. Most of your calculators will not reach 5 digits over 5 digits. It's too much to store. So you already know that your calculator is going to spit out a decimal. How often in calculus do you get 5 digit over 5 digits? You don't. You only get that in probability. So discrete math and statistics are the only math classes you're ever going to have where you get astronomical numerators and denominators at the same time. And at that point, you don't even care about the fraction, you just give the decimal anyway. So, going back to here. The definite integral that you're evaluating, you do the inside first, because if I try to do the outside first, it will change something. Now, because my outer limits are constants, my final answer has to be a scalar. What if my outer limits were functions? You're not going to do problems in general in this class where that's the case. That is the case in other classes. If my outer limits are functions, then my final answer would be a function. Okay? So the order I do things is huge, how I do things, but in the end, I am still just integrating. Now, in Calc 1, we get away with a lot of really bad habits sometimes in a Calc 1 class, particularly if you had it in high school. Oh my goodness. I mean, the stuff I see, I was like, your instructor showed you that? Well, no, they just never told me it was wrong. I get a lot of that. Like, but yeah, you can't do certain things. The whole point of an integral, the integral symbol, space, dx. This is considered just one symbol. This is the operator. If I said d dx, space. If you have a graphing calculator and you do d dx, it's going to automatically give you the open parenthesis, isn't it? Then you're going to insert the argument, the thing you want to take the derivative of. If you know how to do the graphing calculator and you do integral, it's going to probably do, again, open parenthesis, dx, assuming you're integrating with respect to x. This is called the integrand. Well, the why, in Calc 1, why did my instructor, mark me wrong, you got me when I just left off the dx? Because the most important part of any integral is not that. It's that. This is infinitely more important than that. And now you realize that. Oh, now that I know partial derivatives, I have a function, I say, Zachary, take the derivative of that function of 7 variables. Zachary's, sure, Mr. Brown. The problem is you have choices, don't you? That was a bad question on my part if you had choices. No, take the derivative with respect to this variable. That's the key. Okay, I want you to integrate this thing with respect to this variable. Calc 1, it didn't matter, but that was Calc 1. Now it always matters because there's always going to be multiple choices. Oh, and it absolutely matters which one I do. So, do something really simple. This is the kind of thing we have to be aware of in Calc 3. There's nothing wrong with this question. It's even a common thing. You do indefinite integrals in Calc 1 and 2. In fact, in Calc 2, you hardly ever did definite integrals because you were learning methods of integration. The definite integral is just one more step to give me a numerical value at the end, but it was all about doing the correct integration. So both of these should be functions. Well, what's the answer to the first one? What's the answer to plus? Arbitrary constant. I'll put C1. Ooh, that's weird. That is totally weird. So now here's the question. True or false?
Yes,
True. But you can't factor a variable out of an integral. You can't factor the independent variable. And in Calc 1 and 2, you only had independent variables. Oh, can I factor a variable out of a derivative before I differentiate? Yeah, if it's the other variable, because we're treating it as a constant. What are you treating x as in the second integral? As a constant. Can you always factor a constant out of an integral? Yes, that's why you're not cheating. That's the instruction. That's not a y, so therefore that is actually looked at as a constant. Now, I'm not saying you should do this. There's no advantage. You're just taking an extra step. But it's understanding that that's actually what's taking place there. Now, there's a question that I do in Calc 1 every semester. Because substitution, most calculus students can do integration, but they're not very good at substitution in general because they never really learn the rules. So there's a lot of bad technique, a lot of answers that actually equal something completely different along the way, and then somehow we manage to get the right answer, but we have like 8 different things that it equals in the end. This is a question that I do in Calc 1 because we need it in Calc 2 and then we need it again in Calc 3, okay? Because we do forms of substitution all of the time. Because we're starting integration today, you're going to run into situations where you may have to do substitutions. And I'm going to remind you of some of the things that you can do seamlessly and some of the shortcuts that you actually can take. And they're things that really you should have been exposed to in Calc 1, but maybe you weren't, or maybe you were, you just forgot it. I mean, is that a possibility? That you forgot something in life? I don't know how many of you remember everything you've ever learned, but I don't think any of you. I'm pretty sure there's no one alive unless, I don't know, unless they have a photographic memory. It's kind of hard to remember everything because there's only so much storage. Now, in the first one, this is a pretty simple one. We would say, let u equal x minus 2, so my du is just 1 dx. This is what is called a linear substitution. A linear substitution is always the easiest to perform because your chain rule factor is a constant. But it's not always the easiest to recognize. So if I do this substitution, then this becomes the integral of what? Square root of u, or just, how about u to the 1/2 du? And that's, oops, sorry, 2/3 u to the 3/2 plus constant, which is 2/3 x minus 2 to the 3/2. Great. Okay, now, if in Calc 1, every time you did a substitution, you needed to physically show the substitution. You needed to write it out, because otherwise it means you're just doing stuff in your head. And when you're first learning it, that's dangerous. It's not that it's wrong, it's just not a good technique. But now you're in Calc 3. This is what I do in Calc 3. I say, all right, let u be this, let du be this, and then you know what the next thing I write? It's this. Because I'm integrating u to the 1/2 du, and the antiderivative is 2/3 u to the 3/2, and that's what this is. So in other words, now that you've gotten good at it, you're still doing the substitution, you're just not necessarily writing the in-betweens because it's really this one. Really simple. Now, what are you going to do here? You're going to let u be, it has to come from there because my argument is not an x. My argument is a function. That's the only place that the substitution can come from. So then what's my du? It's 2x dx. So all I need is a 2. I just doubled the size of my integral. What should I do?
Half on the outside.
Put a half on the outside. Exactly. So now what have I got now? I now have 1/2 the integral of u to the 1/2 du. Do you all agree with that? It's 1/2 the integral of u to the 1/2. What's the antiderivative of u to the 1/2? 2/3. So that's 1/3 x squared minus 2 to the 3/2 plus c. Or I can write the in-between. Absolutely correct. If you're not comfortable, do this, integrate, back in. So these ended up being almost identical problems, didn't they? Now I got the third problem that looks just like the first one, and well, no, it looks actually, or maybe it looks just like the second one, or is it kind of a hybrid? This is the one that most calc students cannot actually do. But we have to be able to do this one because this is one that will show up often in many different forms. I still only have one choice. So now, tell me what you think. I've been teaching calculus ever since Professor Newton gave me permission to share his stuff. You know, ever since that apple hit him in the head, he was never quite the same. But I've been teaching this for a long time. I would say 95% of all calc students do this. Are you okay with this? Please say no. What I just did is the only common error that people do in general in substitution. I just did something mathematically impossible. I have the old and the new coexisting. In other words, when you change a variable by substitution, it is mathematically impossible to have the new variable and the old variable coexisting. In other words, you have the independent and the dependent at the same time. Because if what I wrote was true, that means I can technically factor the x out, can't I? Because I'm integrating with respect to u. So do you know what most calc students tell me the answer is? This. Nothing could be further from the truth, by the way. This, as we like to say in my house, you can't get any wronger. That's a word. But it sure looks like that's legal because that's a Calc 3 move. Yes, but in Calc 3, I have multiple independent variables. How many independent variables do I have in this problem? 1. U is a function of x. X and u cannot coexist in the same problem at the same time. Absolute impossibility, because if they did, then you would, every substitution you ever did, you would get a completely different answer. Oh, that means you can't do that. But yes, it's exactly what you had to do. U substitution is a very specific form of substitution that you learned in Calc 1. U substitution only works if I have the chain rule factor or at least a scalar multiple of the chain rule factor as part of the integral. That's it. There's no exception. I cannot do a U substitution. What if that was x to any other exponent? Could I do a U sub for this? No, I'd have to try something else, maybe an integration by parts or something more complicated. U sub only works if the chain rule factor is part of the integrand. I have an extra variable there. But in Calc 2, you learned multiple forms of integration, none of which were U subs. In fact, do you remember doing the trig subs? Oh gosh, yeah. But in a trig sub, what did you do? You said let x be some function of a trig. You know, let x be tangent theta. You didn't say let this big quantity be u. No, you said I'm going to replace the x with a function of something else. Then I'll replace the instruction of dx with another thing. I often refer to that as kind of backwards substituting when I first show you, and then I tell you later, no, actually it's the main form of substituting. U substitution is sort of the backwards form. U substitution is a special case. We love it, but it is very limited. Oh, there's an infinite number of things I could put here, but only one of them would allow me to do U sub. But any exponent I put here, I can still go forward and do this problem. I'll show you how. Put any exponent you want here. We can still do this problem from beginning to end. Might not be easy. So the let x be a function of another variable is actually the most prominent form. That's the ode. It's like, oh, that's the only way you can do this problem. But we don't often see that because I said a linear substitution is the easiest to perform, but often the hardest to recognize. What does this become? Can I do this problem? Yeah, just distribute the u. Now, we can finish that. Point being, you're going to do things of this nature, but you have to remember some of the details. U subs are great, but you can't always do things U sub. Now, one of the things about this course, we don't do a lot of integration techniques. I think most students tell me at the end of Calc 3, I said, how many parts, integration by parts do we do? The answer is usually a number pretty close to 1, like the whole semester. How many trig subs did we do? Usually none. How many partial fractions decompositions did we do? Usually the answer is none. You guys remember evil trig? You affectionately remember it? How many of those do you do? Probably never again. Nope. U sub and fairly simple stuff, because the point of this course is not to learn new techniques of integration. It's to take what you already know and then just expand it with application. Differential equations, you're going to use a lot of these things. Parts is something you're going to use. Partial fractions decomposition, by far the most common, as it turns out, because of the nature of the problems you end up looking at. So when we're doing things that may involve a substitution, we don't want to forget the rules and end up doing something, crazy. Now, I would like to find the volume, okay? Bounded by, how about 2x plus 3y plus z equals 12. in the first octave. In the first. Well, it may be helpful to give a rough sketch. You never have to draw things, but primarily, if you end up integrating in the XY plane, you definitely want to know what it looks like, right? And this is a fairly simple shape. I'll do it right here. Six units out in the X direction, 4 units in the Y direction. Oops, 4 Y's over here, and then maybe here. Okay. What is this shape? It's in the first octave, so I'm bounded by the walls. So I took a plane like this. I took a plane and I sliced it this way. I have a 3-dimensional solid here. Do you know what that is? Tetrahedron, good. If you said triangular pyramid, you'd be correct. But more specifically, it's a tetrahedron, which is a fairly friendly shape, but we want to do it from a calculus standpoint. So now, I have this shape. It's clearly bounded. Now, I have 3 choices. Do I want that to be the floor and where it hits here to be the ceiling? Do I want that to be the floor and where it hits here to be the ceiling? Or do I want the XY plane to be the floor and where it hits here to be the ceiling? Most of us would go for the last one because our brains orient things that way a little bit easier. You are correct. Does it actually matter in the long run? No. It never matters when you have choices which one you pick, because in this case, it's a linear function. I don't have any, there's no advantage to going any other way. So I have to solve for one of the variables. You all decided we're going to solve for Z. I want my floor and ceiling to be this way. And that actually is the best choice, but not for the reasons of conceptual, more the reasons of coefficients. If I solve for X, I'm going to have fractional coefficients. If I solve for Y, I'll have fractional coefficients on the variables, but if I solve for Z, I won't. And that actually should lead the reasoning. Will fractional coefficients be a problem? No, but now I got to do integrations with fractions, and maybe I got to square stuff, and the algebra is going to be the same, but the friendliness of the coefficients will not be the same if I have fractional coefficients. So because all of these were linear, it cannot matter what order you do it in. So you're going to say, I'm going to solve for Z because it's the only one that won't lead to fractions. Okay? So we're going to write Z equals 12 minus 2x minus 3y. Does that make sense? That's why we're going to go that way. Now that means that when I do this, right, I'm kind of thinking it's in a this orientation. All right. I now, oh, by the way, what's my floor? Isn't my floor the XY plane? So my floor is Z equals 0. So here's what the volume looks like. Floor minus ceiling. And I'm going to write dA generically, because I haven't decided yet. Now, this is the part you have to draw. I now need to figure out what it looks like in the XY plane. All right? Can anybody tell me what it looks like in the XY plane?
It's a right triangle.
It's a triangle. Oh, okay. And what is the triangle? In the XY plane, the value of Z is 0. So in the XY plane, I have 2x plus 3y equals 12. Okay? That's a triangle that looks like that. It goes forever, but we realize we're only in the first quadrant. Right? We're this guy here. So that would be 0, 4, and that'd be 6, 0. Heck, if I'm putting coordinates here, then again, that's 0, 4, 0. That was 6, 0, and that was 0, 0, 12. Not a bad idea to label things. Now, horizontal rectangles, vertical rectangles, doesn't matter. Clearly does not matter. In fact, there's no advantage either way. So which way does everybody go? Vertical, because again, it's a comfort thing. Are you more comfortable setting it up with verticals? Yeah. Does it make any difference? No. Will it make it easier in the long run? Actually, no. But it's a comfort thing. What makes it easier for you to conceptualize? Because now, if I solve for x, I'm going to have a fraction here. If I solve for y, I'm going to have a fraction here. But most of us agree that, you know, the vertical rectangle orientation is just a comfort thing. So we'll go like this. All right, then I need to write this as y equals what? If I solve for y, what do I get? Four minus 2/3 x? Does that look right? Ish. Something like that. If I had gone horizontal, would have been just as good. So we've now decided how we want to do this problem. We've decided dy dx. How do I know? Because y is ranging from line to line, and x is going to range from constant to constant. Had I done horizontal, then x would have gone from line to line, and y would go from constant to constant. Okay? X is going to go from what to what? 0 to 6. Y is going to go from y equals 0 to y equals 4 minus 2/3 x. Again, you don't have to, but it might be a good idea. Just, you know, at first. I could care less if somebody writes x equal y equal for the limits, but if it's something that you think you might have a problem with at first, put that down. You're less likely to put things in the wrong place. After a very short time, you just get really used to doing things. You won't need to do that. So my first integration, and I'm going to mentally, that's your first integration, is the inside. You don't have to put brackets, but like I said, mentally put brackets there, because this will equal 0 to 6 of now the antiderivative. But because I'm integrating with respect to y, it's not going to be the same thing as with respect to x. Okay, so what's going to be my antiderivative?
-3/2 y squared.
Well, let's go left to right.
12y.
Don't want to lose that guy. So it's 12y
Minus 2xy.
minus 2xy
Minus 3x.
minus 3x y squared. It is not uncommon when people integrate this that they only have one term. If I said differentiate the argument with respect to y, would the first two terms produce zeros?
Yes.
Yes. Oh, but when you integrate a constant, don't you get constant times variable? When you differentiate a constant, you get 0. So a common error that people make early on is, and by the way, they do this in Calc 1, when I say do the antiderivative, some people accidentally differentiate. Because we're still kind of confused sometimes. That's okay. But if I differentiate this rather than integrate, it's going to obviously change everything. But if I'm integrating 3 terms, I can't lose anything. There's no plus constant because it's a definite integral. And now I'm going to evaluate this from here to here, and this is going to go in where the y's currently are. Okay? So I'm going to get 0 to 6. Now, there's a lot of algebra. If you've been in my classes before, the one thing I hate writing is integral equals integral equals integral equals integral while I'm doing all of the algebra within my integral to simplify. I want to write integral equals antiderivative. I want to go forward. Do you agree there's a lot of algebra I need to perform about right now? I need to do 12 times this, and then minus 2x times this, and then minus 3/2 times the square of this. Yikes. Okay, I'll write it out. I'll write it out. I've got 12 times 4 minus 2/3 x minus 2x times 4 minus 2/3 x minus 3/2 times 4 minus 2/3 x quantity squared, all dx. Now, I can distribute, I can square this, and I can distribute, and I can gather like terms, but I'm going to write integral equals integral equals integral equals integral while I'm doing all this algebra. So what I do I'm going to take all of that mess and clean it up off to the side so that the next thing I write is going to be this. I want all of this done here, but I can't do that in one step. Okay? If I could, I would, but it's too much going on there. So off to the side, I'm going to have what? 48 minus 8x minus 8x, then what? Plus 4/3 x squared. Then minus 3/2 times the square of that, which would be 16 minus 16/3 x plus 4/9 x squared. Now when I distribute that, that's going to be minus 24 plus 8x minus 2/3 x squared. All right, so how many x squareds do I have altogether? Looks like I haven't messed this up entirely. I have 4/3 x squared minus 2/3 x squared. That's 2/3 x squared. How about x's? I have a negative 8x, a negative 8x, a plus 8x, so that's minus 8x. And constants, I have a 48 and a minus 24. Now you can see what I mean by I have this equals this, but I don't want you to do this in your head. You can make mistakes. Just, off to the side maybe, but that's what it is. Now we want to integrate that mess. Okay? Hopefully we can do that. Okay, so what are we going to get?
-4.
So, didn't? Say again?
-4.
-4. We're integrating this with respect to x.
Oh, sorry. My bad.
You get a little too ahead of it. Now, just to make sure, before we continue, I want to make sure we don't have any mistakes. Okay, mistakes are below average. We don't like mistakes. That's 2/3 x. Okay. And we have 12 times 4 minus 2/3 minus 2x times 4 minus 2/3 minus 3/2 times the square of that. I just want to make sure, but I don't want to get to the end and it not work and we go, what went wrong? 16/3 and that's 4/9 thirds. Okay. All right. Does everything look okay to everyone? Okay. You have to understand, I'm the only one that can't see. That's why I have to step back. I have tunnel vision. You guys see something. And please, by the way, if you see a mistake, don't hold on to it. I've had that class where we use all 3 boards and it's like, it's not working and so on. And then Masashi says, oh, right back there on step 1, you made a mistake. And you waited till now to tell me, I didn't want to interrupt the flow. If there's a mistake, please point it out. I'm the only one, literally. Right? If I could keep the number of errors on one hand, I was doing well, right, Liam? I'm the only one that can't see the mistake. I'm praying that you guys catch it. So if there's something wrong, always point it out. All right, I'm integrating this guy here, so what do we get? 2/9 x cubed? Yes?
Yeah, minus 4x.
So minus 4x squared
Plus 24x.
plus 24x. I just didn't want to keep going if there was an obvious boo-boo. Now, get your calculator out. This is a piece of cake. You may have a number?
48.
48. I think we did it right. Okay. Now, when you, in Calc 1, when you hopefully derive things like the volume of a sphere by doing rotations of axes, and you did things and you got the formula that you already knew you were supposed to get. or you did the calculus of a problem, and we've already done that, where I already knew what the answer was going to be ahead of time. Do we know the answer to this before we started? Do we know this as a geometrical thing? Yeah, it turns out actually we do, but it's kind of an obscure one, but it does come up. In fact, in linear algebra, it comes up somewhat often. And in our class, we haven't really done this. Remember, we cross product. We had parallelograms and triangles, but this is 3D. So this is a formula I would like you to know because it actually does come up. Not so much in this class, but it does come up, and it does come up in linear algebra, actually. It comes up in a couple situations. So if I asked you, what is the volume of this room? This room is a rectangular prism. Agreed? Now, I'm going to go over some simple geometry because, as I always say, large percent of calculus is entirely based on geometry. And often we forget that. So we know that the volume of a prism is essentially the area of the base times the height. That's a really friendly thing. But if I said prism, is it necessarily this shape? This is a rectangular prism. Okay? A lot of you have had chemistry, pretty sure. Do you use things that look like this in chemistry? To refract light, to go over your spectrum and all that. What's that called? It's called a triangular prism. Oh, yes. See, a prism, like a polygon. If I said polygon, do you know which one I'm talking about? No. Oh, if we said cylinder, oh, I have to tell you. So I have a rectangular prism, I have a triangular prism, I can have a hexagonal prism. It's basically, a prism is congruent parallel bases, and all of the lateral sides are rectangles. That would be called a right prism. Imagine these walls were not really sturdy and the room started doing this. That would be bad. Now my walls are no longer necessarily rectangles, they're parallelograms. That's called oblique. So when you hear the term oblique, that means that's bad. Structurally, you don't have oblique shapes. Your roofs would fall on you. So the default, when you say prism, the default is it's a right prism. When you say circular cylinder, think of a PCV pipe. Oh heck, think of a, not PCV, what's the pasta, is it? Penne? Penne pasta. You guys know what I'm talking about, right? I have a PCV pipe and I cut it like this. Well, what if I cut it this way? Oh, now it looks like this. That's called an oblique circular cylinder, as opposed to a right circular cylinder. The nice thing in geometry, you don't have to say right. That's the default. You have to say oblique. Because if I say I have a prism, you're not thinking oblique, are you? Okay. The prism that is oblique, does anybody know what that one's called? The rectangular prism that's oblique? And it's a term we use in linear algebra. It's called a parallelepiped. How many have heard that term before? It sounds made up, I know. It's called a parallelepiped. A parallelepiped is basically your rectangular prism with parallelograms. Oh, so that means the right prism is a special case of the parallelepiped. Actually, they're all parallelepipeds. That's crazy. Okay, so if this is the case, then here's the question I ask in a lower level algebra class, because we often forget it. I have a rectangle, okay? No question. We know the area of the rectangle is base times side. Now, I want to put a triangle in here that has the same base and height. What is the area of this triangle? 1/2 base times height. And by the way, it doesn't come from the rectangle, it actually comes from the parallelogram. But this is an easy one. So now, we're going to have the first ever Math 252 sleepover. And I'm going to get a giant tent, and we're going to put it in here. But the tent is going to completely cover the floor, and it's going to touch the ceiling. So in other words, it's going to do this. Okay? What is the shape of my tent? It's this, isn't it? It's a triangular prism, it's just on its side. So is everybody with me on that one? The tent is a triangular prism. What is the volume of the tent related to the volume of the room? It's half. because the area of the triangle is half the area of the rectangle. So far, so good? Now, at the end of the sleepover, we're going to do like most people do with their tents. We're going to fill it with Jell-O. And we're going to create a Jell-O mold. Now we're going to remove the tent. And now we have this gigantic Jell-O mold. But what I want to do is I want to go to the middle of the room and I want to slice off that portion of the Jell-O and I want to slice off that portion. So I know Makai's already claimed that piece and Newton's claimed that piece of Jell-O, right? So now I've just sliced off exactly 1/6. How do I know it's exactly 1/6? Because what is the remaining shape? It's no longer a prism, it's a pyramid. And you know the volume of a pyramid is 1/3 the volume of the prism with the same base and height. Now, by the way, that's a simple calculus. We do that problem in Calc 1. We derive that one. So now I have a pyramid. So finally, all right, Samuel and Zachary have been arguing over who gets what. I said, okay, I'm going to do my King Solomon thing. I'm just going to split it in half. You each get half. So now I'm going to go diagonally the length of the room. I'm going to cut this pyramid in half. What is each shape? That is a tetrahedron. Therefore, what is the volume of the tetrahedron compared to the prism? One.
You said it was 1/3.
So I couldn't hear what it said. 1/6. That's an actual geometric formula. The volume of the tetrahedron is 1/6 the product of the 3 dimensions. 4 by 6 by 12. What's 1/6 of that? 48. Why? That's a good thing. It means we did it right. Is that something that you may have learned somewhere along the way? Maybe. Is it something that would be useful to know now for math? Yes. It actually comes up more than any other 3-dimensional shape except for maybe a sphere. Tetrahedrons do come up. Thanks. Enjoy your thing. Okay? So that's a good thing to know, but we can also do it using integration. But we could not have done it with a single integral. There's no possibility that a single integral can set this one up. So what are some of the things that we want to be able to do with integration? Well, one of the things is we'd like to be able to change. We'd like to be able to change the order sometimes. Now here's the question. If I have something of this nature here, I'm just generic. I'm going 1 to 5 and y squared to y to the 4th, f of xy dx dy. I have this integral here. I don't want to do this one. I want to reverse the order of integration. This is just a general statement. It's nothing about this problem. What do you think? True or false? For a true statement to be true, it has to always be true. For a false statement to be false, it only has to be false once. So really, I'm asking you a simple question. If I want to reverse the order of integration, I want to integrate in the opposite order, is it as simple as just changing the order of the limits? How do you know that in this case? Well, I'll keep it simple. What is the answer to the first question? It's a scalar. What is the answer to the second question? It's a function of y. It will never be equal, by the way. No, you cannot do this. There is one exception, and there's one exception only. If all of my limits are constant, then it means the region in the xy plane is a rectangle. It's the only way you can get all of your limits be constant is your region's a rectangle. Then it doesn't matter what order you do it. That's the exception, and you're rarely going to run into that problem, by the way, that you're integrating over a rectangle. But that would be the exception. No, you cannot simply reverse. It does not work. So the question is this. How do you do it, and maybe why would you ever do it? So here's the thing. And I'm going to show you a simple example. So I'm going to show you how to do it first of all. You notice I gave you f of x, y, because I didn't care about the actual answer. What I'd like to know is how do I reverse the limits? That's really a more important question. So let's start with something fairly simple. I don't want this So I have x is going from 0 to 3, y is going from x squared to 9, f of x, y, dy, dx. I would like to rewrite this as f of x, y, dx, dy. Here's what I wanted to point out. Both of these should lead to the exact same thing. This is the most generic form of a double integral. I'm integrating over a region in the xy plane, TBD. You guys know what that means? To be determined, yeah. You know, see that, tournaments. So who's in the championship? TBD. All right. I'm integrating over a region in the xy plane, dA. I means I haven't decided which way to go. Well, that's one of the ways I could go. That's the other, which means both ways are completely reliant on that. So what I have to do is figure out what is my region in the xy plane. How do I do that? Draw a picture. That's it. Don't do it in your head. Draw a picture. Well, what picture do I draw? That's crazy. Well, no, it's right here. X is between 0 and 3. Y is between x squared and 9. Is that a hard picture to draw? I don't know, let's try it. I'm showing you this is how you do it. This is not a way, this is the only way. Anything else I'd just be guessing. And the one thing I don't like people to do is don't do this in your head. You don't need to. It's too easy to just write it out. So I need a picture where y is going from y equal x squared to y equal 9. Yeah, how's that? Y equal x squared, y equal 9. X is going from 0 to 3. Did I just capture my region? I integrated dy dx, which means I did this. Now let's do a quick check. Y is going from y equal x squared to y equal 9, and x is going from 0 to 3, because that point would be 3, 9, would it not? Everybody cool with that? If that agrees, then turning it around should be, as long as it's not too complicated of a region, it should be easy to turn it around. Now, in the first quadrant, y equal x squared is the same as what? X equal square root, positive square root, because we're in the first quadrant. See, I need to do this now. So if I do this, x is now going from, and by the way, remember, when you're looking vertically, higher is always bigger than lower. That's why the upper limit, lower limit. But when you're moving left to right, which is bigger, the left or the right?
Right.
The right, because that's the way the number line moves. Oh, so I want to go this minus this. So my right-hand limit would be what? Root y. And my left-hand limit would be 0. And now the y values are going from what to what? 0 to 9. That's it. That's how you do it. If the region itself is not terribly complicated, and it's usually not going to be terribly complicated, because you're going to have functions, scalars. Most of the time. I mean, yeah, I could come up with something that's really nasty. It wouldn't be that hard. Okay? Now, I'm going to go back to a Calc 1 problem that I do. Because once we understand the bigger picture, the details, the integrating things that you can integrate, that's easy. But it's kind of mindless. There's no thinking. Just antiderivative, go on. But sometimes there's a situations. So here's a question I always ask in Calc 1. Okay? Find the region bounded by y equals the inverse sine x. Let's make sure I got my picture correctly. Y equals pi over 2 and x equals 0. Make sure I got my. All right. I want to find this region. So this region, sine goes this way, so inverse sine basically goes this way. It's just flip. So this is what it looks like. Okay? So clearly the area will be, find the, sorry, area. Find the area of the region. Don't just find the region. Find the area of the region. Sorry. So the area is the integral from what to what? This is Calc 1. So when we say that curve minus that curve, and x is going to go, oh, what is that value? Well, I know the y value is pi over 2. Huh. Inverse sine of what gives pi over 2? 1. Because the sine of pi over 2 equals 1. Oh, so that's 1 comma pi over 2. Oh, that makes it easy. Okay, great. Piece of cake. Constant minus inverse sine. So the antiderivative of this is, of course, Houston, there's a problem here. We all know the derivative of inverse sine. What's the antiderivative of inverse sine, or is that one that we don't actually really have? Huh. We're kind of stuck, aren't we? Everything's correct. Huh. Might there have been an easier way to do this? Yeah. And no one ever thinks about it. What if we did it that way? What if I do it horizontally, integrate with respect to y? Then instead of y equals inverse sine of x, I'd have x equals sine of y. Ooh. This is correct. This is absolutely correct. We just don't know what to do with that piece. So how about we do it this way? Right hand, which is x equal sine y minus x equals 0. And y is going to go from what to what? 0 to pi over 2. That doesn't look so scary anymore, does it? It's negative cos y from 0 to pi over 2, which is negative cos pi over 2 plus cos 0. And that answer is 1. Huh. Can you do that? Yeah, what did I start by saying? Every problem that exists in 2 dimensions can be integrated either way. We just set it up both ways. But usually one is easier than the other. Are there exceptions? Yeah, they might both be easy. Right? I might be bounded by lines and things. Often it doesn't matter. This one it clearly mattered. So what I was showing you is, hey, if I rewrite the problem, if I change things, I might be able to do it from a different point of view. This is a Calc 1 problem. This is day 1 of integration in Calc 1 to remind us there's more than one way to do a problem. So this was dead end. This still worked. Now, here's the situation. You are on the job. You have a situation. Maybe you're on a team of people. So my team, Zachary, you collected some of the information, and maybe, I don't know, Nina, you're going to set up the integral, and then Samuel, you're going to actually solve the integral, and everybody's got their own pieces. But the integration, everything was correct. But we ran into an integration we couldn't do. Not because we set it up incorrectly, but because somebody handed us a problem that they couldn't get past. I get questions all the time from students, a lot of former students, saying, I've run into trouble on this problem. How should I integrate? I love that question. I'll say, I don't know, let's look at it for a minute. And I'll say, did you try this? Did you try this? Did you try this? They'll say, yeah. That saves me some time. Okay, well, let's try this. Because the question is just so difficult and so gnarly, maybe they found it online. It was a challenge problem. I have students who actually love doing that, going online, finding challenges. If you can answer it, you get some recognition or something. It's kind of fun, I guess. So the question, everything was correct, and your team member handed you the following problem. So the setup, all the information was there, and your coworker handed you this problem. It's exactly the same thing as saying your coworker just handed you this problem right here. Everybody understand? Same thing. And you're looking at it going, okay, this is correct, but I don't know what to do here, so what did you do? You said, what if I integrate it differently? I started this problem by telling you the boundaries, so you started this problem with a picture, agreed? And then we came up with this, we go, no, let's go the other way, but we already had the picture. You're handed this problem. Well, what's the problem? There's no problem here, except that I have to integrate cosine of x squared with respect to x. I don't have a chain rule factor. And I need a 2x, don't I? You all agree that I need a 2x there? I don't have a 2x there, so I'm kind of stuck. Any ideas? Oh, in words?
Flip it.
Yeah, what if I try changing the order? Huh. Because here's the thing, you're on the job. You need an answer. But maybe, I don't know, maybe this one can't be done. Is it possible you have an antiderivative that can't be integrated? I want to remind people, in Calc 1, did you ever have a question that could not be integrated? No. In Calc 2, often. That's why you learn things like tailored polynomials as an estimation from the things. If you're in my class, we spent a lot of time on Desmos showing the coolness of doing asymptotic convergence of things that couldn't be answered, and we'd come up with as many decimals as you needed, and all would be correct, even though, it's cool. No, for every integral that you can do, there's an infinite number of tweakages of it. What do I mean by that? You can all integrate sine x dx. What about sine of f of x dx? In general, no. Unless f of x is a scalar multiple of x, this probably cannot be done. And there's an infinite number. Oh, sine of e to the x, sine of log x, sine of inverse tan x, sine of x to the 4th power. Nope, can't do that one, because I don't have the chain rule factor. Oh, so it's not an automatic that you can always integrate stuff. But in a calculus class, if you're asked the question, it's cheating, but you probably can't answer it, because otherwise you wouldn't have been asked it. But in real life, is it an automatic? Is it an automatic that I can do this one? No. But I can manipulate the limits of integration. So here's what I know. Y is between this and this. X is between this and this. So I did this right. Okay. So probably the first thing I want to do, I'm just going to draw the line x equals 1/2 y. Okay. This is a positive number. So x equals this would be a vertical line. Do you agree? With me so far? What is that point right there? That's probably important. Root 2 pi. Well, if I put where these intersect, y would have to be 2 times this. Oh, that'd be square root of 4, so that would be, everybody see that? Aha. Okay, and now I'm told y goes from 0 to root 2 pi. Do you agree that that's my region? I'm bounded by vertical, horizontal, and diagonal. I'm bounded by lines. That's pretty friendly. Right? I mean, my y limits are constants. They have to be because it's the outside integral. But my x limits was one constant and one line. So, but the suggestion was to switch the order of integration. Okay. Right now I'm integrating dx dy. Right now I'm going this way. Okay. I want to change it to this way. So I need to rewrite this line as what? Right now it's x equal 1/2 y. Y equal 2x. That's it. That's the only change I need. Aha. So y is going to go from what? Y equals 0 to y equal 2x. X is going to go from 0 to the square root of pi over 2. Now, In general, switching the orders of integration is not trivial, not in general. But I gave you a problem that I can do it. Now, I don't know if I can integrate the result. I have no idea if I can integrate the result. But I do know that I don't care what the question is, call this f of x, y, I can always reverse the order because I can always draw the region. Remember, you're bounded by constants here, so you really only need to figure out what the functions look like. Okay? And that's never going to be something complicated. It just isn't. There's no point. So now we have the integral. Y is going from 0 to 2x. X is going from 0 to the square root of pi over 2. And my integrand is cosine of x squared dy dx. Oh, so now my first integration is with respect to y. I don't need a chain rule factor. So I'm treating the cosine literally as a constant, aren't I? See, there's no y in that statement. So what's my antiderivative? Won't it be cosine x squared times y? I'll put the y in front. I think it reads a little easier. Anybody catch that? Cosine of x squared is a constant with respect to y. I couldn't integrate it with respect to x because I don't have an antiderivative formula for that because they're the same variable. But now it's a constant compared to the y. So now I'm going to replace y with 2x and 0. So this equals 0 to square root of pi over 2 of what? 2x times this minus 0 times this, so it's just going to be 2x times the cosine of x squared. All right. Did this get better, worse, same? Way better? Because now if my u is x squared, what's my du? It's sitting right there. If my u is x squared, then my du is 2x dx. So this is now the form cos u du. What's the antiderivative of cos u? Sine u. I'm just going to go ahead and do it. The antiderivative of cos u du is sine u. That's sine u. Did I skip the in-between? Yes, because you can, because it was right there in front of you. You didn't have to do anything. The chain rule factor, this is cos u du. Now, what's my answer? It's the sine of the square of the square root.
Don't you have to change your balance since you changed your u?
But I didn't actually rewrite the integral. Hold that thought. I'll do that one in a moment. I'm showing you a shortcut that a lot of us aren't comfortable doing yet. So now let me go ahead and I'm going to do it both ways. I just want to make sure we understand. Sine of what? It's a sine of pi over 2 minus sine of 0, which is 1. You're kidding. After all that, it was just 1. So now, Katerina is correct. If I physically change the variable within the integral, in a definite integral, if you change the variable, you absolutely have to change your limits. I'm amazed at how often even differential equations folks don't do that. If I change the variable and leave the old limits, it is a completely different numerical answer. And in a definite integral, there's one thing you never do, which I find that all calc students do. You never change back. You only change back in an indefinite integral. If you substitute a variable in a definite integral, you have to change the limits. There is no problem that exists where you ever change it back because it's a number, not a function. The only reason you changed back was an antiderivative is a function, and it should be a function of the original variable. So when you do a u substitution and you integrate and have a function of u, your question started with a function of x. Oh, I need to change it back to my function of x. But a definite integral, I'm asking, this is producing a numerical value. I just want to state what it is. So I want to do this then as cosine u du. If I put these limits here, it's a very different answer. Because there's no such thing as changing back. Once I put limits here, this is a number. So what limits would I put there? Well, the simplest way of doing it, the notation I always use, I like to use is saying, x is ranging from 0 to the square root of pi over 2. What is u going to range from? 0 squared, which is still 0, to what? The square of the square root of pi over 2. Ooh. We like that, don't we? Therefore, if I physically change the variable, I have to change the limits. And now let's continue. This will be sine u from 0 to pi over 2, which is sine pi over 2 minus sine 0. What we don't do is change any part of this back. That step never existed, and nobody ever showed you that. Even the absolute worst YouTube video, which is not very hard to find bad YouTube videos on math, no one's ever going to show you to change a definite integral back. And the vast majority of all calculus students do anyways. If I have different numbers than this, then this answers to a completely different numerical value. And you can't have a definite integral equal more than one numerical value. Now here's what I was showing you here. Because the chain rule factor was sitting right there and I recognize it, this is cos u. So technically, isn't this sine u? Yeah, but since I didn't physically change the variable, I could see it in front of me. I am giving you license to do this. In Calc 1, I wouldn't let you do this because we're just learning the process. This is legal. This is the only other way. They're both correct. They both produce exactly the same thing at the same place. What I can't do is have a u here, but have these limits here. That would be a different numerical value for an answer. Now, the point of this problem, hopefully you caught, is that this is now a real life situation. I'm in a situation, maybe I'm working with a group of people and we got to this dead end and somebody hands me the problem and says, I don't know where to go from here. And you're going, I don't know where to go from here either, but what if we reverse the order? Maybe that'll help. Okay, and so in this case it did. Will it always work? Not necessarily. We kind of lucked out here. I kind of set it up that way. But in general, that's the reason that you want to know how to change the limits, is because you might take something you can't do and make it into something you can. You would never change the limits to take something you already can do. You would have no reason to change it to something that you might not be able to do. You agree with that one? I'm going to show you one more little trick today, because this is going to come up so ridiculously often, and it's a Calc 1 thing that a lot of us forgot. And it comes up as often as anything, but if I don't know the shortcut, I will end up spending way too long on problems that should be technically simple. Here's a question, it's a Calc 1 question. Okay, every Calc 1 book has this. You know how to integrate each of these functions in general, right? Cosine, e, secant squared, okay. Problem is, I gave you 3 different arguments. So every Calc book will say do the same thing. Break this up into 3 integrals. By the way, there is no substitution I can do on this. Why? Because I have 3 different arguments. So Calc 1 books will say, and by the way, correctly will say, now do 3 separate u subs. And here I'm going to have u equals 2x, over here I'm going to have u equals 4x, and over here I'm going to have u equals 3x. Do those, introduce what you need, do the integration, change it back, you're done, you're correct. Wow, that's a lot of work. Because you should have been shown something else in Calc 1 really early on, but you may not have, or maybe you did, but you forgot. When my argument is a scalar multiple of the variable, meaning my argument is linear. But my argument isn't x, it's something times x. It's not x squared, it's not square root of x, it's not function of x, it's a scalar multiple of x. I want you to differentiate f of kx, where k is any real number. Isn't the answer f prime of kx times k? So if I said differentiate sine of 10x, you'd say it's cosine 10x times 10. We know that. That's not even a question. So the question really is, the following statement you know is always true. You know this is true. The antiderivative of the derivative is the original function, whatever that is. You know that is true. So what I want to do is some slight variation of that. I want to integrate this. I want to integrate. I know the antiderivative of f prime of x is f of x. So therefore, the antiderivative of f prime of scalar multiple of x is probably some version of f of kx. Do you agree? But it can't equal f of kx. I'd be ignoring the k, so we do u substitution. How about if I let u equal kx, then du is k dx. Is that correct? Yeah, that's all I can do. So now I've just made this into 1 over k f prime of u du, which is 1 over k f of u plus c, which is 1 over k f of kx. This is a very simple formula, and you will probably use this more than most things because scalar multiples of x is a very common argument, right? You're working with sines of 2x and 4x and 3x and e to the 5x. You're working with that kind of stuff probably more often than you are complicated functions, which means that all of this is an utter waste of time. I don't want you to do any of this. Is it that easy all the time? Yes. Absolutely all the time. It's that easy. How many have been shown this? You better raise your hand if you're in my class. I'm amazed at how often people get to the highest levels, they weren't shown this, and you're going, you mean I've been doing all this u substitution? Like, I could have just wrote the answer? Yeah, this is actually a formula. And this actually is in the calculus books. It's just not emphasized. Yes, Emma?
Shouldn't that be f prime of x
Did I?
on the right? Not f prime of kx times k, just f prime of x times k?
No, oh no, because you can't change the argument. Think of it this way.
Oh, okay.
Yeah, think I'm going to differentiate
Okay,
the
never mind.
sine of 6x. Now it's going to be the cosine of 6x times 6.
Okay.
The reason I'm showing you this is to say, oh, then if I want to work backwards, we kind of now remember that, don't we? Oh, yeah, so if I'm multiplying, then I want the reciprocal when I go the other way. This is an extremely useful shortcut, and it's always true. If I know the antiderivative of the secant squared of x, then I know the antiderivative of secant squared of any multiple of x. The only thing is that multiple shows up in front as a reciprocal. Why? Because the derivative then gives me that multiplier again. Okay? This, I don't need you to do this, but I hope you do this because the alternative is just too many steps. Okay? That again, we love shortcuts because I'm not cheating, but I'm also not wasting my time. I've already seen people in this class do stuff like this, where they have a fairly simple thing and we make it really complicated because we don't realize that shouldn't be complicated, not that. Okay? This, I believe today, ends the material that is on the next exam. So the next couple things are then further, exam 3. Probably the most important concept, I've already had people ask me about this, next week, Wednesday of next week, Green's theorem, probably the most important thing that we do in this course. And it's not that it's hard, it's that it's not obvious, and so it requires development and things. That's a class that you probably want to try to get to again. I do have videos. And what's interesting, that is the only video that I have that was actually a live lecture from the classroom. Okay, could you let me stop?